Okay, we have started recording. So we are talking about a pendulum, and there is gravity here, G. The length of the pendulum is L. The angle of the pendulum is, we say, is theta of T. Okay, there is gravity, and there might be a torque acting on this pendulum, like this one. Let's call it T of T. The torque acting on the pendulum. This is supposedly a parenthesis. So if we draw the free body diagram of this pendulum, what we get would be the pendulum. Well, I'm not separating the pendulum, I'm just writing it. There are the reaction forces. Let's say if this is point O, let's say this is OX and this is OY. There is the mg force that is downwards, and that's why there is a torque also, T of T. This angle is, we said, is theta. This distance is L. This is L cosine theta, and this distance is L sine theta, as you can see here. Basically, we are going to write a moment equation, and that would be enough. You can just write the summation of moments about point O is equal to IO times alpha, alpha being the angular acceleration. Well, we assume that this connecting rod or rope is massless, so IO is the moment of mass moment of inertia of the pendulum about point O. IO is simply, since there is this mass here, it is ml squared, nothing else. Using parallel axis theorem, if you like. Okay. IO is ml squared. Then we will just write summation of forces, summation of moments. We have written that, the moments that act on this point about point O is, let me write it here. And the moments, we will write it as summation of moments about O, let's say counterclockwise being positive, is equal to, there is the external torque, T of T, which is counterclockwise. Well, there is this mg, as you see, downward, has a moment arm of L sine theta minus mg L sine theta, because it is clockwise, rotating clockwise, so it's minus, is equal to I alpha, I0 alpha, which is ml squared. Alpha is, as you know, is the second derivative of theta, theta double dot. So we can write this as ml squared theta double dot plus mgl sine theta equals T of T, or divide everything by ml squared, and we get theta double dot plus g over L sine theta equals 1 over ml squared T of T. Okay, now we have a problem. We have this sine theta term. This sine theta term makes this equation a nonlinear equation. This is a nonlinear term. What do we mean by that? The nonlinear term, sine function, as you know, is theta versus sine theta, is a function like this. So it is, it is not a linear function in terms of theta. If it were linear, this would be linear. But this is nonlinear, obviously. So what do we do? Well, first of all, I didn't say this before, but in this course, we are trying to deal with linear equations to keep it simple. That's the main reason. Nonlinear equations are quite common, but we try to look at linear equations for two reasons. One, for that to keep it simple. Secondly, we can approximately linearize nonlinear equations. So that's what we will do. We will say that sine theta is approximately equal to theta. Let's say for small theta values. And this theta should be in, by the way, in radians. Okay. The natural unit for angles is not degrees, but radians, as you know. So for small theta, how small? We can say that theta should be less than, let's say, pi over 6, which is something like 30 degrees. Okay. So if theta is below 30 degrees, you can kind of approximate sine theta also for negative values. In this range, you are approximately in the linear range, okay? Approximately, not exactly, but the error you make is not too big. In that case, for small angles, for small oscillations of the pendulum, you can assume that your equation of motion is theta double dot over g over L theta is 1 over ml squared t of t. Okay. So,
Hocam,
yes.
I'm so sorry to interrupt you, but may you explain how we define small, like for system, like
The deviation from, sine theta and theta should not be large. For example, I don't know, let me try to compute it, for example. I have a, calculator here. Let's say 30 degrees. Sine of 30 degrees is 0.5, right?
yes,
For example, 30 degrees in radians is pi over 6. So what is pi over 6? Let me calculate that. Pi over 6 is equal to 0.523. For example, pi over 6, which is, let's say, theta is 0.5, what was it? 32? 235 or something like this. Well, whereas sine pi over 6 was 0.5. So what is the difference? Well, not too much. It's like 4% or something. And after that, it grows as you see the difference. So approximately, if you can tolerate 4% error, you can represent a non-linear system with a linear one. Okay.
okay. So we are talking about this difference between the actual value and the radian value of it.
So this is
it's not about yani şey gibi değil hocam, işte 0.5 işte sin 0.5 küçük bir değer. Evet, bunu kullanabilirim gibi değil de aralarındaki fark gerçek değeriyle işte radyan değeri arasındaki fark küçük diye şey yapabilirim.
the difference between them is small.
Okay hocam. Thank you.
We will be talking about linearization. So this is the approximate linear differential equation. The thing is, we need the linear equations in order to be able to solve them. Now, linear equations are not easy to solve if you can solve them. Many nonlinear equations are unsolvable, actually, whereas linear equations always have a solution.
One
So,
question, did we also convert the theta double dot into the radians, or did we only convert the sine theta into radians?
no, theta should be measured in radians. Theta double dot should be in, if you want it, its unit should be obviously radians per second squared. Okay?
Okay, thank you.
Okay. Um, this would be our equation, and we can represent the system is if you replace by d by dt by s, you can write the transfer function of this system, which would be s squared plus g over L, let's say theta of s would be t of s divided by ml squared, and the transfer function between, let's say, theta of s divided by t of s, approximate obviously, because we have the linearizing approximation, 1 over, let's say, ml squared, s squared plus g over l. Okay. This would be our transfer function for this system. Okay. What if we had, this is the pendulum, what if we had an inverted pendulum? What is that? We mean the pendulum stands upwards like this, okay? So, let's say this is the vertical, and like this. Now this is theta. As you can guess, this pendulum is going to fall down. Okay, it cannot stand still by itself. G is downwards. This is L, and the equation of motion for this pendulum, I'm not going to derive it. It is that the this torque of mg sine theta won't be restoring, it will be separating it from, by the way, we have a theta, we have a torque, let's say, T of T. The equation of motion for this system will be theta double dot minus G over L sine theta would be equal to 1 over ml squared T of T. The only difference is this thing. And this means that the system is unstable actually by itself. It is unstable because the theta value cannot, reach an equilibrium. It will eventually drop. It is an unstable equation. We will come to stability later on. I'm not going to, go into details of that. Again, you can linearize it and approximate it, etc., etc. No, that's not a big problem. Okay, so this is we have introduced the pendulum and the equation and the linearization. Now, we have said that we have translation in systems. We have also rotational systems, but quite often we have their combinations. So we might have translation plus rotation in a system. Let's look at that one, how we deal, and I will give you the simplest possible example. So you have a mass spring system, but the mass is it's not a good drawing. It's it's a circle, let's say. And let's assume that there is contact here. And this is in contact. So here you have, let's say, no slip between the ground and the disk. This disk has a radius of r. This has a mass of m, and inertia, mass moment of inertia of I, let's say. And the coordinate we describe this is x, but there is also the rotational coordinate, theta. Well, I couldn't draw it very well. This is theta, okay. Rotational coordinate. And no slip basically means that there is a kinematic relationship between x and theta. No slip means x equals r theta. X and theta are related to each other. Okay. That is, x and theta are dependent with each other. So translation and rotation are combined through this equation. And not only this, but we can take derivatives. So the second derivatives are related as well. X double dot is equal to r theta double dot. We have, we have means of combining the translational and rotational equations here. Now, what does no slip mean, by the way? No slip means that this equation is obeyed, definitely. By the way, can you have no slip with no friction?
No, hocam.
No, you cannot. There has to be some friction if you want to have no slip in your equation. Okay. So if you want to draw the free body diagram for this system, well, we are going to draw it only for let's say we have moved an amount of x, and there is the friction force. Let's say that we have the friction force F is in this direction. Okay. X coordinate is like this. There is the theta rotation. Let's call this point O. Now this should be equivalent to, there is the translational mx double dot, and there is the rotational, let's say I theta double dot. Inertia force and inertia torque, as you know from 301, for the ones who have taken it. Now, one more thing is, what is this value of F? You remember that F was equal to, well, in some friction cases, if there is dry friction, F is equal to mu n or something like that. So can we take F is equal to mu n? That's a tricky question.
No need, hocam, I think.
No
need to take it as...
It is not no need. It is, well, F is not equal. F should not be equal to mu n. You should remember this. F should be, if there is to be no slip, should be less than or equal to mu times n. Or, well, we should say mu s times n. Actually, we won't be using this equation. But if there is no slip, the friction force should be less than mu s times n. This is if there is no slip, let's say.
But hocam, it's going to be equal to mu kn, right?
No, no, definitely not. For the no slip condition, it should not be equal to mu k times n. If there is slip, it should be equal to mu k times n. Okay.
Hocam, another confusion. Can we use the words slip and slide interchangeably, or they're different?
Yes. slip and slide are more or less the same.
Okay.
No slip is the translational equivalent of no slip is as follows. There is the friction force. Let's say that you have a translational thing and you push it with a force F, okay? Let's say you have an M, and this is, the friction force is F, okay? As long as, you see, if this thing is not moving at all, as you know, no motion means F is equal to small f, right? As long as F is less than or equal to mu s times n, there is no motion. So as long as the friction force is less than mu s times n, there is no motion. Now, how is this related to our case? You see, no slip means that this point is you remember from dynamics that this point, the contact point C, is the instant center, okay? And the velocity of this point is 0, okay? So there is no motion only at the point of contact, which means that, well, if there is no slip, the velocity of this point of contact should be 0, which means that we are in the, well, our case is very similar to this one, the one that is, let's say, translation. Anyway, so this is our free body diagram. This is the friction force. We will just keep the friction force as F, nothing else. So we sum up the forces in the x direction. And, well, this is the positive x direction. So you have minus kx minus F. Okay. Well, let's put some, maybe we should just put a force here so that there will be an external force. F of t. So the forces should be equal to mx double dot. Okay. What else do we have? First of all, there is the moment about point O. Let's say is, if you take moments about point O, it's just F times R. F times R is equal to I times theta double dot, right? Or should I say I? Yeah, I. But I can say I0. It doesn't matter. I0. Inertia about 0.0. So we have two equations, 1 and 2. But actually, we should have just one equation here. It is not a 2-degree of freedom system. It's a single degree of freedom system here. The third equation we have is that x double dot is equal to r theta double dot. Okay, this is our third equation, which is the kinematic equation or compatibility equation, whatever. Now, there is something we don't like here, and that is this F force, this thing, as you see. We don't know what it is, plus we don't need it, so we can just eliminate this. We have too many equations. Actually, we can, using those equations, we can eliminate them. For example, you can say that theta double dot is equal to FR over I0, I naught, okay? And we have x double dot is equal to R theta double dot. So I can say x double dot is equal to the double dot over r. Maybe let's not use this. Sorry about this. Let's erase this. And I can use the following. Sorry, not x double dot, but I'll try to eliminate theta double dot. So theta double dot is equal to x double dot over r. That's what I should write, right? Yeah. Okay. Therefore, x double dot over r is equal to fr over I0, or x double dot is equal to fr squared over I naught. And we want f actually. F is equal to I naught x double dot over r squared. And now we can write this put it into 1. If you substitute into the first equation, you are going to get f of t is equal to mx double dot. Let's collect the x terms together and rearrange them. We have so this is the equation of motion in terms of the coordinate x. Okay. So this is the equation of motion in terms of the coordinate x. We could somehow eliminate the coordinate theta from here, but we can write this equation in terms of theta as well. Since x and theta are dependent, we have x equals r theta, x double dot equals r theta double dot. So you just substitute these into those equations, and you are going to get m plus I0 over r squared r theta double dot plus k r theta equals f of t. These are, well, r's do not. What do we get? Not much else. I guess this is the equation of motion in terms of theta. If you like, we can multiply everything by r to get r squared, so that it will be a little bit better looking. It will be I0 plus mr squared theta double dot plus kr squared theta equals r times f of t. Now everything will be in terms of torques here. You see, everything have the units of torque. This is a better version of this equation, okay? So this is another possible equation that represents this system. So you can have, for example, a block diagram like this, in which f of t is the input and, sorry, f of s is the input. And x of s is the output. And you can take the transforms and so on, and you are going to get the following transfer function. M plus I is not over r squared.
Hojam, isn't it gonna be I naught r in the formula because you multiplied with r? So before it was I naught over r squared.
You mean this one? This one? Or this one?
Yeah. Oh, yeah. The first formula you multiplied it by r, right?
Everything by r, yes.
Yeah. So it was I naught over r squared. So when you multiply by r, so it's gonna be I naught r instead of I naught.
Yes, but this here you have an r here, as you see. So this will be r squared. And r squares will here, this r squared and this r squared will be canceling, okay?
Oh, okay. Oh, thank you.
So if f is the input, x is the output, this is the transfer function you will be getting. Well, one more example, a rotational system. I'll just go through some examples. I think that is the best way. With a long shaft, let's say that you have a motor that drives the system, and you have an inertia. That you rotate. And let's say that this inertia is in a bearing. And here you have a long and not so thick shaft. So this is a long elastic, let's say, shaft. So it's only thing is it is not rigid, so it has torsional elasticity. Secondly, here you have, let me use another color, some strange color here, so that you have damping here in the journal bearing, let's say. Okay. So the method here, the motor has a certain rate of rotation. Let's say this is theta I. Okay. The motor has a rotation of theta I, and this shaft that has an inertia of I, let's say, has a rotation of theta, not theta I, but theta. So you have a damping in the system. We want to model this system. And this shaft, as you see, is acts as a torsional spring. So this system, we can model it by the following model, which will look a little bit strange at first sight. There will be some torsional spring which represents the shaft. Then there will be the inertia. Let's say this is the inertia, the spring of the shaft. This is theta I, is the one end of the rotation. This end is theta, is the rotation. Now between the ground, as you see, and the inertia I, there is damping, rotational damping. So we will represent this by a element like this, between the ground and this thing is BT, let's say. Okay, torsional damping. So this is torsional stiffness. KT is torsional stiffness. And BT is torsional damping. It is a simple system, obviously, but it's usually it makes people get confused. That's why actually I try to give this example. What do we do for this system? We write the equation, draw the free body diagram for the inertia. Now let's say that we have taken the direction Now this is the kind of the trickier part. I will try to explain. The torques that are acting on this system, okay? The torques that are acting on the system are Kt times theta I is the input torque because of theta I. Kt times theta is the rotational torque because of theta. And Bt times theta dot is the rotational torque because of theta dot. Now, since this is confusing in terms of rotations, try to imagine this like a translational system, like this. It is much easier to do it this way, to imagine it this way at least. So you have, let's say, theta I is here, theta is here, and that's all. This is Kt, this is Bt, and you have an inertia of I, okay? If you were writing the forces, not the torques, but the forces, you would be writing the following. Kt times theta I would give you a force in this direction, okay? Kt times theta would give you a force in that direction, and we're giving you a force in this direction. I'm just writing down the rotational equivalence of these. So this is the translational equivalent.
Hocam,
Yes.
what is the theta I?
Theta I is the input rotation that comes from the motor, this one.
So is the I a subscript?
Yes, it's a subscript.
Okay. Okay, thank you.
So Kt times theta I gives you a torque in one direction. Kt times theta gives you a torque in another direction. Okay.
May you explain I again? I'm so sorry.
Theta I is the input and input angle, basically, okay? I is a subscript. Theta input, let's say.
So the last theta is just different than the first one because of the damping. Is it the case?
No, it is this theta and theta, theta I and theta are different because of the spring. Because that the shaft is elastic. If the shaft were not elastic, they would be the same.
Okay.
Theta I and theta would be the same. But since there is a spring between them, in terms of a shaft, theta I and theta are different quantities. Okay. Do you understand that?
Yes. Thank you.
Yeah.
Hocam, how does KT produce two different torques?
Well, it doesn't. We decompose it into two different torques. You see, there are two values. One is theta I, the other is theta. If you think about it, let's look at this example. I'm showing it here. Okay. Theta I goes in one direction. Theta and theta are in the same direction. Let's say that I keep theta constant. Okay. And let's think about forces, not the torques. If theta were constant only, without theta I, theta I being having a motion, you would have kt times theta I produce a force in the rightward direction. Okay, this one. Whereas if the opposite happens, if theta I is 0 and theta has a certain rotation or a motion, you would have a torque in the opposite direction, like this one. So they are in the opposite directions. Since there are two possible coordinates, and each coordinate creates a torque in different direction, or if it were a translational thing, force in certain direction, in opposite directions. Do you understand that?
So is this because the two different theta is like two different displacements at the different ends of the spring?
Yes, there are
Okay.
two different displacements, yes.
Thank you.
So, the summation of we can do the following if you want to see, if you have, let's say, take the first case, let's say, we are going to do a superposition. If theta I is 0 and theta is not 0, okay, in that case, the torque Tk would be, Tkt if you like, would be minus kt times theta. And the second case being, if theta I is not 0, but theta is 0, in that case, Tk would be kt times theta I. And if you make the superposition, well, this is not a real summation, but it's a superposition. Tk is kt times theta I minus theta. Okay. Let's not think about this as a addition, but superposition. Okay. And this is the trickier part of this problem. So if you sum up the torques on this thing, it will be kt times theta I minus theta minus et times theta dot is equal to I over theta double dot. So I O theta double dot plus et theta dot plus kt theta is equal to kt theta I. So this is the equation of motion. And if you do the usual Laplace transform trick, you get your output is theta of s divided by so this will be the transfer function between this is the output angle, and this is the input angle. Okay. Okay. Let's take a break here for about
Hocam,
yes.
may I ask something about the superposition thing?
Yes.
So like we said, theta I and theta are like connected to each other, like because of the spring, it just changes, like theta I differs from the theta because of the spring effect.
Yes. Yes.
So like how can theta I can be zero when theta is not zero?
No, we assume that it is zero. Well, we just superimpose them on each other. They cannot be zero, obviously, and you know. We just assume that there are two different coordinates. We assume that one coordinate is stopped. We try to find the effect of one of them, and then we stop the other coordinate, and we try to find the effect of the other coordinate, and then we add them. I think
Okay.
we propose them, since that's our, this is a linear system. Linear system superposition works.
Okay, hocam. Thank you, hocam.
Okay, you are welcome. So let me stop recording.